Okay, the next speaker is Rodrygo Santos from Universidade Federal de Minas Gerais, and the paper is Online Learning for REC for Sequential Music Recommendation.
Hi everyone, I'm Rodrygo Santos from the Federal University of Minas Gerais in Brazil, and this is a joint work with lots of colleagues from UFMG. This was done by a master's student of mine a couple of years ago. So the idea here is how we could adapt online learning to approaches that were proposed for search for a sequential music recommendation scenario. So we're precisely looking at something like this. We want to produce somehow a playlist continuation given some initial input. So precisely we have a seed song to take as original input for the user, and we want to produce some reasonable music continuation of this playlist. Normally this could be done either manually by some form of expert curation, or also automatically by some form of machine learning on past user behavior, for example. But in both cases, we have a static playlist as a result of this process. I mean, regardless of what happens during the user's listening session, the generated playlist is going to be the same. And that might be the ideal, the desired situation, because we could have preference drifts along the way. It's well known that users' preferences are influenced by context, for example, changes of mood, changes of the activity the user is performing. And ideally, we would like this playlist generation process to be reactive, to be dynamically reacting to the user's feedback along the way. So we could somehow explore alternative paths throughout the available songs in the listening platform. And one area that is particularly suitable for this kind of dynamic adaptation of ranking is contextual bandits, which is the basis for what we're doing here. One problem, though, is that traditional contextual bandits approaches, they work at the item level. They try to estimate rewards for items as arms, and that may be a problem. For instance, in the case of Spotify alone, they reported recently over 30 million songs in their catalog, which is a huge number to be able to learn user preferences along the listening session. So instead, we adapted some form of what is known as continuous armed bandits in some scenarios. So essentially, instead of modeling items as arms, we represent each of the songs as a feature vector, and then we instead learn ranking models as potential arms whose reward we want to estimate along the way. In this particular case, as is the case in current practice for online learning to rank for search, we're using linear models, so we're essentially talking about a weight vector W as our target to be estimated. But the problem is, we actually need to estimate this model and update along the way as the user interacts with the system throughout the listening session. So for instance, you could have an initial model choose among the available songs what is going to be recommended as a continuation for the user's listening session. And then after the user gives some feedback on top of this recommendation, the model can be updated to produce the next recommended song, and so on and so forth as we go along the way here. But the question here is really, how can we do this model update efficiently enough so that we converge to something useful for the user during the listening sessions, so we do not just explore forever to learn about the user's preferences. Oops. And for this, we built upon another variant of bandits, which is known as dueling bandits, which is particularly suitable for this sort of feature-based representation of items. So just to give you an illustration, let's say we have a two-dimensional feature space with two features, 1 and 2. We could somehow project our current model W on this same space. And to update this model toward the next interaction with the user, what we do here is we explored the vicinity of this model in the space. So we randomly sampled other candidate models in this vicinity, in this case the model highlighted in blue. But then we need to somehow estimate whether the sample directions are promising ones. So essentially we need to come up with some way of estimating the reward of each of these candidate models and compare them to the current model W in red in here. Normally how this is done in search is through a process known as interleaving. This is done to avoid building up on presentation bias in click data. So just to give you an illustration of how this is done traditionally, we have interval candidate models produce a ranking. In this case, the current model produced this red ranking, and the candidate model produced the blue ranking. We interleave these two rankings in a sort of round-robin fashion, and show this interleaved ranking to the user in a blind fashion, so the user doesn't know exactly where each result came from. And we collect feedback on this interleaved ranking. In this case, usually clicks. And we can then propagate the reward back to the original models that produced those results. So in this toy example here, the blue model would get 2 clicks and the red model would get 1 click. So we would say that the blue direction is a promising direction that could be incorporated somehow in the update of our model W. But we have one problem here. There are many problems with it. One problem we have with this issue is that it could be particularly slow to explore one direction at a time during a listening session. We may not be able to learn fast enough to come up with good recommendations for the user while he's listening. So instead, to avoid exposing the user to bad recommendations along the way, we try to maximize what we can learn during a single interaction with the user, doing what is known as multi-dueling bandits. So instead of trying one candidate direction at a time, we try multiple directions at a time until we all these rankings and learn infer somehow their estimated reward. But then this is search. In our particular scenario, which is music recommendation, instead of showing a ranking to the user, we don't get to do that. We only get to show one music, one song at a time. We only have one spot to collect feedback, which is a problem because we have many models contributing or competing, or dueling, as we call them, at the same time, and only one spot to collect feedback for all of them. So in this case, what we proposed is what we call it counterfactual dueling bandits, which is an idea of trying to estimate what the model would have done should it have a chance to show its recommended song to the user. So essentially, our counterfactual question here is, what if the user had actually been recommended each model's top choice, which is the #1 ranked song in these 2 rankings here? How do we go about actually estimating these rewards? We adopted a very simple heuristic here based on the well-known reciprocal rank measure from information retrieval. So basically, we look at the rankings produced by these 2 models and try to see where the actually recommended song, so that the user actually saw where this song is listed in these 2 rankings. So in this example, it's in the 4th position for the red ranking and the 2nd position for the blue ranking. So according to reciprocal rank, red would get 1/4, which is 0.25, and blue would get 0.5 for the 2nd position. So again, that would be considered a promising direction. And finally, the last issue we have is the fact that we're not anymore dealing with click feedback. We're dealing with binary feedback in this case, plays and skips. And in the case of a play, because it's somehow noisy, we don't know actually if the user liked it or not. We are playing conservatively, so if the actual song recommended by the current model was played by the user, we just keep the model as it would give it the highest reward, so it cannot be outperformed by the other models. Otherwise, if we get a skip, we incrementally decrease the current model's reward. So gradually it gets a lower reward, so eventually it's going to be outperformed by one of the candidate models. And because this promising direction is promising in the sense that it's ranking better, which is actually a bad sign because it got a skip, we want to actually move away from that direction. So essentially the update would just result in the current model moving farther from the candidate direction. So just to go quickly through several of the results we got, we tested for learning convergence in terms of time and also effectiveness at convergence, and also the impact of the number of duels we perform along the way. We used a traditional data set from Last.fm, enriched with other data so that we could produce a feature-based representation of our models. We split this into time windows so we can have different samples from the results. And quickly, to operationalize this evaluation, we picked actual user listening sessions with the songs they listen to at each point in time, and we enriched this with to simulate unbiased feedback. We enriched this with each of these test cases with randomly picked songs, so another 99 random songs picked from each of these points. So the task here at each point in time was to find the actual song liked or played by the user. I don't have time for this, so we used standard features for 22-dimensional feature vector representation of the songs, and we compared a model against linear UCD, which was presented in one of the previous talks, which is a state-of-the-art contextual bandits approach, but models items as arms instead of models as arms as we're doing here. So quickly, for our first research question, how fast we can learn so we can give the user good results faster. You can see here, the top curve is actually an oracle, and the second from the top is our model, and the other ones are the baseline. So we can see essentially that our model, which we call CDB, gives the best performance at all times during the session, and this is averaged across all sessions in the data set. Another way of looking at this is that at any given payoff level on the y-axis, we reach that payoff level earlier than the competing models, which is good, so we can produce good results faster. And at convergence, we actually showed with this result here that we converge to a better model than the baselines also. It's on a fixed tailed offset. And finally, the idea of introducing multiple competing models at each interaction with the user, it was worth it. So this essentially shows that the more models we explore at each point in time, the better for the results. And just to sum up, we introduced a novel online learning direct approach for sequential music recommendation. This is based on implicit feedback, which is different from most of the work done before on this particular view. And for the characteristics of the problem, we had to resort to some alternative way of estimating rewards because we didn't have a ranking at our disposal. And as extensions, we did a very simple use of positive feedback because it's quite noisy. We could invest further in that direction and also apply this to other scenarios. Thanks. If you have time for questions, I'm happy to take them. Otherwise, please come by the review session for RecSys 2020 later today during the closing ceremony. Thank you very much.
Okay, we have just 1 minute for a quick question. Okay, over there. We don't have time. It's almost 5. Okay.
I didn't plan it that way. Sorry. Hey, thanks so much. I can see a ton of applications for this. Hopefully this will be a quick question. How do you estimate in a reasonable way how far to move in the other direction?
That's a good point. In the little example I showed you, the actual exploration occurs in the vicinity of the current model, so we have a hyperparameter to essentially give the radius of that sphere.
Okay.
And we also have another parameter which we call exploitation parameter, to decide how much of those potential directions we want to incorporate back in the current model.
So you just move all the way to the radius in the other direction?
Up to what this parameter lets us do.
Gotcha. Thank you.
Okay, thank you very much. Thanks again.